Hello, my name is Daraja Brown and this is my Lab 3 video report. In this lab, I use physics principles and computational models of a star, black hole, spaceship, and planet. The purpose of this lab is to explore the connections between force and momentum decomposition and their implications for the other basic physics principles we've discussed thus far, such as mass and velocity. I drew knowledge from multiple principles throughout this experiment, especially these shown on the screen. For Lab 3, I used Python to create the computational models for Part 1 and Part 2. I also used Google Sheets in Part 1 to calculate the average mass of the black hole and to generate a graph showing the different mass values generated by the Python model. For Part 1, I ended up calculating the average mass of the black hole to be 6.96 times 10 to the 33 kilograms, and the graph on the right shows the different values of mass for each data point throughout the star's trajectory around the black hole. For Part 2 of the lab, I ended up with an initial velocity of 2.12 times 10 to the 8 meters per second in both the x and y directions, and 0 meters per second in the z direction. For Part 1, which had the objective of finding the mass of the black hole around which a star orbited, the first step in performing this was to identify the system and surroundings. My system, for the majority of this, was the star, as I calculated the net force of the black hole acting on it through its motion and change in momentum in order to eventually link it back to the black hole's mass. The black hole was the surroundings, and the initial conditions were randomly generated by the trajectory assigned to my star, but the mass of the star and the time interval of 1 day are listed here. As you can see from my code, the majority of this part was to update the starter code provided to us to accurately calculate the net force on the star from the black hole every day. I input given values for the mass of the star and delta t, but used my own knowledge of physics thus far to update momentum and to find relationships between parallel, perpendicular, and total momentum and net force. I also derived the formula to calculate the mass of the black hole, or MBH here, by rearranging the formula for the force of gravity being equal to the net force. Finally, I updated the arrow information at the bottom in order to have arrows representing the direction and magnitude of the net force and its parallel and perpendicular components. So again, here are the results of Part 1. The average value for the black hole's mass across all 501 data points, or days, was 6.96 times 10 to the 33 kilograms. And as can be seen from the graph, the data was fairly constant, but it could have been more precise if delta t was a smaller interval of time, since 86,400 seconds was pretty large. My system for Part 2 was the spaceship, since I was calculating its initial velocity, which was influenced by the planet and black hole, which were the surroundings. The initial conditions for Part 2 listed here on the right include the mass of the black hole that was calculated in Part 1, as well as the mass of the spaceship and planet, and delta t. The initial speed and velocity of the planet were also given. The coding for this part of the lab mostly involved calculating the net force on the star and planet due to the gravitational pulls they experience from each other as well as the black hole. I then used the velocity and position update formulas to create the trajectory of motion for both the ship and planet over time. So in the end, my initial velocity for the spaceship was 2.12 times 10 to the 8 meters per second in both the x and y directions, which I calculated by taking a value slightly less than the speed of light and breaking it up into x and y components based on an angle of 45 degrees. This result was pretty different from the goal of remaining close to the black hole, although my initial velocity caused a successful trajectory in terms of not colliding with the planet or getting sucked into the hole. Perhaps this trajectory was not close because the x component of the initial was positive, but if it was negative, the ship would have been moving towards the hole more from the beginning. Net force is numerically equivalent to the rate of change of momentum, as is the sum of their parallel and perpendicular components. However, their relevance and role in this lab was different. We could model and calculate the change of momentum and its components over time because we had the necessary variables and values, but we could not calculate the net force directly. Thanks to the momentum principle, we could extrapolate it through its relationship to delta p over delta t. To create an orbital motion of the spaceship, I came up with the initial velocity of -3 times 10 to the 6, 6.7 times 10 to the 6, and 0 meters per second through trial and error. The x component is somewhat smaller than the y component and it goes in the negative direction, so this caused a more elliptical motion, yet it is much more round than my initial trajectory. The code below shows how I included this velocity, and for the y component, I used the same code used to generate the planet's initial speed. So in conclusion, as demonstrated in this lab, force and momentum decomposition can be extremely helpful in relating the two and filling in gaps for understanding and predicting objects' motion, especially in centripetal situations. Thank you.